I'm just going to go briefly over questions that you got wrong or some people got wrong. Yeah, this one here. The basic idea of this question was I was actually asking you to prove Shannon's channel capacity theorem. Okay, that was the essence of this question. And so if you divide this guy into two parts, whatever B is, whatever it is, it defines the number of symbols per second. Okay, whatever it is, it will result in. Now, some of you said some of the separation between frequencies. That may not be false, but what I was looking for was I was looking for the rationale in the proof of this theorem. And so as far as I can tell, when people prove this theorem, this B term boils down to how many symbols per second you can send, okay? And then this term here, this term is basically how many bits are in each symbol, okay? So that was basically outlining, in my mind, when I asked this question, was I was outlining the two fundamental steps in proving this theorem. Okay, that one, you got that one right. This one, you got right. Some of you got this wrong. Yeah, go ahead and look that up. You can go ahead and memorize that because you'll be seeing spectrums all the time. You can memorize what that means. Yeah, here. Oh, I should have, yeah, see, I changed the question. You notice the question's changed? See, that was the, yeah, or should have been 9 grad students and 1 professor. But I didn't want to do that because I didn't want you to think I was going to be the PAN coordinator. Yeah, so okay, so this is the one where you pretty much got it right. I mean, I didn't take off a lot, but these 2 arrows here, the arrows that cross through 0 are the bad ones. Okay, so I made a PowerPoint, and this PowerPoint is significantly bad for a couple of reasons. Well, here's the same figure. Okay. Now, obviously, those are exactly the same waveforms, and so they're going to have exactly the same spectrum. It's just when you these transitions here on this bottom one occur when you go from, when you go from 45 degrees down to minus 135 and back again. Okay, so this is a 45-degree phase shift to a minus 135 back to a 45. That's what this bottom waveform is. And it has a bigger discontinuity. Now, the whole G part of phase shift was to smooth out those edges. And so this is, if you saw this picture, and obviously I created this picture in Excel, which looks a lot like this picture, but it is fundamentally wrong because, as you know, the frequency here is 500 megahertz or 800 megahertz or whatever, but the symbol rate is closer to a megahertz, right? So if I had done this correctly, this picture would have had hundreds or thousands of waves, at least hundreds of waves before there was a phase shift. Okay, so when I hit the Fourier transform on these 2 waveforms, I'm not going to get anything realistic, but I am going to demonstrate the fact that the top. Okay, what do you expect to see? Let me, that'll be an interesting question. I'm going to take the Fourier transform of the red ones. Okay, you see I added a little window so that the transform wouldn't have spectral leakage. So the blue waves, the blue signal here was this one, but I added, you know, a window to line it up. What do you expect the frequencies response of these two to be?
Can't even tell there's a blue line anywhere.
No, that's right. You see at the edge, right there. Oh, that was the answer. Fine. Can't even see this. Okay, fine. It's linked. But all right, so it's okay. Ignore the blue line then. I'm going to take the transform of the red line. Okay. What do you expect it to be? The whole essence of this question was what? What was the whole, and it was the whole section of phase encoding. What did we want to do when we phase encode? We want to send bits, but what limitation did we have?
Discontinuities.
The discontinuities caused what? What did the discontinuities cause?
High frequency components. That's unwanted.
Okay, not just high frequency components. Be more be more specific. If my carrier frequency is 500 megahertz or 433 megahertz, what does the phase shift do?
I mean, it broadens the spectrum.
Broadens the spectrum. Thank you very much. That's exactly what happens. Okay. Now, this particular data isn't correct because there should have been hundreds of waves per symbol. But it illustrates the point that in this case here, the dark blue lines are the ones that went from 45 degrees to minus 35 back to 45, whereas the gray one went 45, 135, minus 135, minus 45. That's what the gray one did. And so there was less broadening of the spectrum. Now, because of the fact that there weren't hundreds, it broadened a lot. But nevertheless, that was the point of this particular question in the exam, was the broadening because of the lines going through. Anyway, that was the point of that. I think that was this one did fine.
Can you go over 6?
6. Okay.
And what each of them
in your
actually
defense,
are?
you could build a data storage unit. We add a digital logic, right? I guess we need, okay, so let's first make the analysis, okay? So what is in a communication system, what is the analogy between energy? Energy is related to what? What parameter is correlated to energy? When you transmit energy across space in a communication system, what are you doing? What are you communicating across space? Okay. This is a very
Information.
Information, yeah. A communication system transmits information across space. Okay. By encoding it in energy. Okay. So if I were to ask what type of system transmits information across time, the question would be easier, right? Which of these transmits? So you had to make the analogy between information and energy, okay? And then ask the question, what system transmits information across time? And then I would charge, pick a, you know, if for example, a ROM memory. How does a ROM memory work? A flash ROM. what do you do? How does a flash, what is the physics of a flash ROM? How does it store information?
It puts a charge on.
Yeah, so they're
Capacitors.
two base transistors back to back, not connected to anything, and there's charge or there is not charge. Okay, and so that information, okay, is a collection of charge, which I will contend has energy. Okay, what about a magnetic tape? Or a physical platter disk drive? How is energy stored?
Magnetic charge or magnetic.
Charge, again, a magnetic energy is placed on the media. And then what does that energy do? In both cases, that energy is transmitted across time. So the information is encoded as energy. Energy is deposited on the media. The media then exists across time and then is decoded at some later time. And so,
Is magnetic tape like across time though?
of course,
Like,
it is.
isn't it across like a magnetic tape? You don't need a sense of time, right?
Yes, you do, because you write it. How do you use a tape?
I don't know, honestly.
You record onto it, and then what do? Do you throw it in the trash?
Is there
I think
no
these guys
specific
have used.
places like for a
Yeah, sure.
magnetic?
There's a place, okay? There's a place on the tape where there's a bit. You deposit magnetic energy onto a tape.
Yeah. So are there sections for a bit on a tape?
Absolutely.
So it's not across time, but
Oh, yes,
rather,
it is. How is it used?
I mean, you spin it up at a constant time, but you can also go slower and read it slower. So it's not across
But
time
the
necessarily, but
essence of
space.
the essence of the data storage unit is you write to it, and then you wait a couple of minutes, days, years, decades, and then you read it back. And energy has transmitted across time. If you
Oh, I
lose the
see.
energy, right? If you store charge on the base of a flash transistor and that energy is lost or corrupted, you've lost your data.
So why is digital logic wrong?
Because
So
there's no
digital
sense
logic
of time.
transmits what over what?
But there's no time, and there's no
I thought it meant
effort.
like SPI, like you transmit it and you clock in things.
Yeah, but it's not storing anything. Yeah, but SPI is a communication system. Okay, I want to take a bunch of energy, and I
No.
stick it
Data storage
someplace,
makes sense now. No, it
and
does. Like,
I wait a year, and I go back and look at it. I've stored data.
no, that makes sense. Yeah.
Okay, sorry. It's the cool part is all the crap about encryption, encoding, decoding, security. That all applies to both signal to noise ratio, error detection, error correction. All of that, all of the math in a communication system can be applied to a data system. It's just you have to swap space and time. Right? So why would you compress data in a communication system? Right? To increase bandwidth. Why would you compress data in a storage system? To increase data storage. Okay, sorry, enough. That was, yeah, no, that's a fun thought thing. Okay, I think I'm done. Yeah, no, here, yeah, you got this one. Okay, that's fine. I'm done with that. Okay, all right. All right, answer that one. I'm done with this one. Obviously, I did not expect you to do a fast Fourier transform, but we did talk about how the transitions across the the edges transitions through zero would cause the broadening of the spectrum, okay, which is what Austin said, and I agree with that. Okay, so let's remind ourselves what we needed to do. Okay, I'm going to remind myself here. This one, no, I need, yeah, okay. All right, so I have two polynomials, okay? Okay, let me quit this. Here's another one that's a little bit unintuitive, okay? So we're going to classify two polynomials to either be one is bigger than the other or one is not bigger than the other, okay? So we're not really going to say, are they equal or are they less, okay? So we're going to, so even if something that looks like this, right, where you add a term to it, we're not going to say that this one is bigger than that one. These are not, no one is bigger than the other. Okay, so we're not going to, saying they're equal is probably not the right thing. These three are not bigger than each other. Okay. Because they all have the same, so the only thing that matters is the coefficient, I mean, the exponent of the largest term, the largest exponent, okay? And again, this is a 5 and that's a 4, and so this one is bigger than that one, okay? So this little symbol here means not bigger, okay? Okay, not bigger. Not necessarily equal, obviously not less, but not bigger, okay? So it's not equal, it's not less, it's not, okay, so because when we get to the subtraction, okay, here, we have to know whether or not to be able to subtract, okay? So right here, because these, let me go back, stop this, go back one. All right. Because I'm comparing these two right here, okay? And because I'm only going to subtract if the blue is bigger than the black, okay? So in this case, I didn't subtract, right? And so there's a couple of things to note here. The polynomial I'm using in my CRC has what property? I don't know if you can see it. What can you tell me about all the polynomials? All right.
Are they odd?
No. Oh, yes, they are all odd. Yeah. That's a true statement. They are all odd. Okay, fine. Never mind. There's my answer. The polynomial is going to be defined such that its most significant bit is a 1. Okay. And we're going to adjust the W such that so if, for instance, to be the coefficient of that largest term, And therefore, when we write out the polynomial, whether it be 2 bits or 32 bits or whatever, or 64 bits, the most significant bit will always be 1 in the polynomial. Okay? And so therefore, we can do a fairly simple decision about whether to subtract. You notice I didn't subtract here, okay? But I did subtract here. And I did subtract, and I did subtract here. And I didn't subtract there, but I did subtract here. Okay. And I did subtract there. So what do all these cyans have in common? I subtracted if. And compared to the ones I didn't subtract. Okay, so obviously it's the same number of bits, right? So I have a 5-bit polynomial which has width 4. Okay, and so therefore I'm going to line it up and either subtract or not subtract. So what determines whether I subtract it or not? What's the characteristic between the cyan and the red?
Width of the polynomial.
No. The width of the polynomial is 4, but how is the cyan different than the red?
I mean,
See the pattern?
cyan all has the most significant bit set.
Yes. Okay. So in order to decide whether or not to subtract, since I know the polynomial will have 1 in the most significant bit, all I have to do is look at the most significant bit of wherever I've aligned it. Okay. And if the most significant bit of my dividend has a 1 in it, I'm going to subtract the polynomial. Okay. Here's another thought. Whenever I subtract, need another color, purple. Or whenever I don't subtract, either way, I guess. Okay. Okay. Right here, it's gone. What happens? Okay, I missed it. I made a mess here. Whatever. Whether I subtract or I don't subtract, what happens to the most significant bit of the dividend? You see it? They're all zeros. So I don't have to store it, by the way. We're going to see that. All right, so let's go on to the next. All right, so this is a very inefficient and very useless and very but illustrative for what we just said. Okay. The first is, okay, let's couch this. This is a W equals 4 cyclic redundancy code on an 8-bit message. And the polynomial is stored as a 5-bit, most left aligned constant. So there's my 11011 left aligned. My message in this case is simply an 8-bit binary, and the remainder is formed, the dividend, if you'd like, in the subtraction, right? So you go over here, there's the dividend. That's the message starts out as a dividend, you subtract crap off and it becomes a remainder. Okay. So the the variable here, remainder, is both the dividend while it's in flux and become the remainder when we're done. Okay. And it's an 8-bit message, so I'm going to do 8-bit, do it 8 times. And you remember the reason, Caleb said it, and I think somebody said it. We're going to decide whether or not to subtract if the most significant bit is a 1. Okay. That's this line of code right here. So if this line of code right here decides whether or not the most significant bit is 1, and then the subtract operation is the same as the add operation, which is implemented with an exclusive OR. Okay? And then rather than shifting the polynomial off to the right, it shifts the dividend off to the left and does it 8 times. Turns out the remainder is up there in the most significant 4 bits. And luckily for me, I ran this code on this data and got the 4. So I'm optimistic there's not too many bugs. Now, obviously, I took it from here, but I don't know. I structured it a little bit. I might have. Okay. So in this case here, the polynomial, okay, is this. That's the polynomial, and the width is a 4. Okay. Now it's obviously pretty useless. It's only an 8-bit thing and a 4-bit mesh. So this one is a very inefficient version of the same thing, except it's much longer. Okay, so we can take any message which is formulated in bytes. So you can't send 102 bits. You have to send a power of 8, but you can send any number of bytes. It also works. This particular code is obviously set up for 8-bit CRCs, but because of the type def, it would work for a 16 or 32-bit CRC as well. Now it's got a couple of fun things. First of all, if you look at the order, okay, there is a test right here and then a shift. In this code. Over here, it's going to do the shift first. Okay. Four byte, that's the bytes right here. Okay, take it back. That's the test first. Okay, never mind. This is the same. It's the slow version. Never mind. It's the next one that does the other opposite. There's the test. And then it will shift, but it either will subtract and shift or it will shift. Okay, fine. Sorry. So the polynomial here isn't shown on the slide, but it's this constant. Okay. And the how many bits wide is this? The same as that. Okay. So this is either an 8, 16, or 32-bit shift and an 8, 16, or 32-bit polynomial add. Okay. And so here, this is a combination. So it takes the next byte, sticks it in the back of the remainder, shifts it over, and then adds another one in there. Okay. So this is doing a byte at a time. So again, the hallmark here is the most significant bit of the remainder tells you whether or not to subtract, and the subtract is an exclusive OR. Okay, so so again, I'll say it again. This one does a test followed by a shift, just like the other one. That's the slow version. The fast version, okay, is going to do two things. First of all, it's going to pre-calculate all the possible 8-bit to 8-bit conversions by having a table here. Right? And so since it's doing a byte at a time, you're going to take a new byte out of the message and then chunk it, calculate this, and store it into this table. So it's going to pre-calculate what this will be and calculate the remainders given any 8-bit dividend. You see, this is an 8-bit dividend here is all the possible 8-bit values. It's basically going to do that function in the previous thing, but pre-populate this table. And now we can go faster. Okay. Now, and so what it does is it takes the entire takes a byte out of the message here and looks it up and then shifts this part over because that's the previous byte, and then exclusive combines it and gives you the remainder. So the idea here is just going to go faster by pre-populating. Okay. Yeah, this is one of the slides I was looking for, and that is the polynomials here. Now, it doesn't look like the most significant bit is set, but it turns out in this algorithm here, this polynomial is if you have a CRC. If you have a CRC 8, in other words, W equals 8, it's a 9-bit polynomial. And this is only the bottom 8 bits of it. And so when you look up the polynomial, for instance, that's why it's called a truncated polynomial. The actual polynomial is 0x18005. Or over here, 0x104C11DB7. So again, the initial the highest bit doesn't have to be saved because I will always, if I exclusive OR it, I will always set the most significant bit to 0. So it only actually does the subtract or the exclusive OR with the. Okay, so this is W equals, okay, and this is a 32-bit polynomial. There's a couple of confusing not confusing. There's a couple of sort of adjustments that they do in order to deal with some special cases. Rather than starting with an initial remainder of 0 here, okay, you could start with something else. So for instance, if the entire message is 0, in other words, if you had a dropout and the entire message were 0, the remainder is going to be 0 and it's going to look proper. And so what they do is they preload the remainder with something other than 0. And in that way, they can handle cases where you've got a big long line of zeros. Another one is the fact that this stuff was designed in the 60s, by the way, if you remember. And if you remember from your 319K days, a UART sends the start bit, but what is the first bit in a UART after a start bit? And then the stop bit. Right, so if this is the start bit, and there are 8 bits of data here for a UART, which bit is this? It was on the 319K final. I don't know, you chatting it? I can't see. I don't have my chat open. No. Unmute yourself. Tell me what bit that is. That's 2 choices. It's either a 0 or 7. Come on, brave person.
The least significant bit.
Yeah, so this is bit 0. And so therefore, some of the original CRCs back in the 60s implemented what's called the reflected data. And that way they do it in reverse because the data showed up in reverse. But, you know, that's what reflect data means. Here's some special cases. Like I said, a whole bunch of zeros. And so, you have to be careful that a bunch of zeros could be an actual data in it. And you know, that could be an actual correct answer, or it could just be a dropped channel. And it turns out if you like I said, if you preload the remainder with something other than 0, you can differentiate lost data from you know, just real data with zeros in it. Yeah, now I've already said that because of the UARTs. Okay. There was a check parameter, and the check parameter is a way to verify those are the remainders you get when you send in a standard standard parameter. So if you send in a 9-character ASCII message and run your algorithm, this guy here, this checksum with a standard value should match the table down there. That was just a way for you to verify your stuff. Keyshawn noticed that all the polynomials were odd. And that is actually and so if the polynomial if the 0th bit of the polynomial, G is the polynomial, is a 1, then and then a 32-bit CRC can detect an error on a burst length of 32 zeros. Okay, so this is one of the reasons to increase the size of the polynomial to handle longer burst errors. So a sequence of errors that is one after another. So every bit is wrong for 32 bits long, can be captured by a 32-bit CRC. So this is sort of obvious. I mean, as long as you have 2 bits set, you can detect, as long as the G has at least 2 bits, then any 1-bit error is going to show up twice. Okay. It's fairly easy to get detecting 2-bit errors. And that is, I don't know, there was a big long description of it, but basically, yeah, a multiple, right? So G and H are a multiple. Oh, good. Okay, so if you can add, if you can formulate G with a combination of these, okay, then it won't detect it. But if you look at this, right, this CRC here, 1 1, bunch of zeros, okay, bunch of zeros, 1 0 1, that there is not a way to add these up, okay, and get that, okay, and so therefore it will detect 2-bit errors. You notice that all of these codes have an even number of bits that are 1, and that will get you 3-bit errors, 5-bit errors, 7-bit errors, 8-bit errors. So there's actually, these codes were sort of created. Oh, it was in this thing, yeah. Yeah, where was it? It was in, yeah, this one. No, it was the Wikipedia page. Anyway, these codes were created, and then a bunch of math came around, and people decided that they were not, yeah, that one. They were not perfect. So, like I said, there are these all these codes, and these aren't necessarily the best, 16-bit codes that are out there, but they became standard. All right, enough of that. All right, get to the end, right? Yeah, no, this way. All right. I don't know. That'll be a fun thing to do. All right. Questions on CRCs? Okay, so when Keyshawn comes to office hours during the exam, if Keyshawn comes to the office hours prior to the next exam, he's going to ask me, what is the most important thing of this slide?
I will not be coming. I will be exempting the next one.
Okay, so it's Keyshawn in his stead. Okay. Which Keyshawn will decide to do lab 5, so he doesn't take the next exam. Good job, Keyshawn. The rest of you can follow his liking as well. But if you were to reflect on this chapter, what are the fundamental takeaways? We're trying to do what?
Error detection.
They're trying to error detection. And what are the 2 fundamental descriptions of an error detection scheme that will improve our ability to error detect? We have 2 knobs in our error detection scheme creation, and we want to do what 2 things?
The number of bits used for the error code allows a higher number of
Sure.
higher detection.
And the fancy word for that is called width. Okay. All right. What's the second criteria of an error detection code that makes it more robust?
Use division, introduce chaos.
Chaos. Okay. Now, CRC is just one way, right? It's just one thing that is very chaotic. That is that is why CRCs have been adopted, because they are chaotic, which means that they have a better chance of not having false negatives, right? Multiple errors that come out as a correct checksum or correct error code. Okay, so those are the two, and chaos is defined to be how much does each bit in the message affect each bit in the checksum. Okay, how much is there a mixing of the bowl, so to speak, so that all the bits are affect all the other bits. Okay, all right, so those are the two fundamental principles. Hamming distance is a way to now obviously the trouble with hamming distance is if you've got 1,000-bit message, you have 1,000-dimensional space around which to calculate hamming distances. And so, although the principle is valid for any number of bits, the practicality of hamming distance is I don't know how many 1,000-dimensional space graphs you know how to draw, but I don't. Okay. All right. Let's see. Oh boy, do I save it or not save it? Let's just, all right. Yarabali and I created a MOOC. We put a Wi-Fi example in there. We created some videos that explain how to do stuff. We're going to fetch weather from a server on the internet in this slide, at least to illustrate the process of using a Wi-Fi connected device to fetch information off of a cloud. Okay. And so one of the things that I wanted you to be able to do when you do a lab was to put your finger on some of these concepts. In other words, the Wi-Fi device connects to the access point, the domain name system converts a ASCII string into an IP address. We're going to open a socket which will have the IP address and the port number and the type in there. So you'll see that UDP and TCP have the same sort of format, the same sort of six-step sequence, except UDPs are a different type of socket, obviously, and the transmission is different as well. And then when we're done, we can either send another TCP or another UDP, or we close the socket. Okay? So I want you to, when it comes to passing a test, what are the fundamental steps associated with each of these six steps? And so this is an example. On the top is the payload, the ASCII payload, which is sent as a TCP packet. This bracket X is this bracket X here is a code you got to sign up for, but let's see, that's just a placeholder. And so basically this is an ASCII string that you're going to send to openweathermap.org, and then that TCP packet is going to then the weather server will respond with another TCP, which is, it's got, depending upon what time of, obviously that's 5 years old at this point, but basically sends you what you asked for, and that is the weather. It's called JSON, is the symbolic language that these TCP packets and responses are following. Okay, so embedded in there that it's where where did I get the information from? You know, Austin. What was the weather? Cloudy. 15 degrees. Okay. But what I want to do here is, oh no, okay, no, this is not the right one. All right, ooh, okay. So this one's an animated GIF that goes through all the steps in a very, very direct way. I want to do this slowly. Yeah, there we go. Okay. Oh yeah, let's go back. So basically, this is a cartoon showing two clients interacting with the same server, both asking for the weather, okay? And so what you want to get out of here is that there's really, in this client server protocol, there are two types of sockets. One is an open socket, a port 80. When you first connect up to when you first interact with openweathermap.org, you are given access. Well, you send a connection request to openweather.org through port 80, and it goes through their connection socket. So con socket, a socket is a data structure through which you can communicate. Okay? And so the server at this point created a connection socket that's open for the world and waiting for clients to happen. So, okay, so it created a connection socket. Okay, so there is a connection socket on the openweathermap.org server that is internet facing. Okay, again, a socket is a data structure through which it can communicate. And all you need to know is the IP address of the server, and that's port 80. Okay? So, and now it's doing nothing. Okay, so it's waiting for a client to make a request through that connection socket. So we're going to turn on a microcontroller called client A. This is an edge device somewhere around the world, and we're going to create two of them just for the fun of it. Okay, it could be 1,000, right? But I don't want to draw 1,000, so I only drew two. And so now I'm going to run A in front of B, but obviously there's nothing special. One of them goes first. One of them is turned on first, or they're turned on exactly the same time. It don't matter. It would work. So it's going to create a socket, obviously internal to itself, okay, called a client socket. Again, a socket is a data structure through which it can communicate. Right? And so there's going to be two client. Well, for as many clients as we got, we're going to have that many sockets. Okay, and so inside of client A will be a connection socket. Now, if you want to get the time or some other resource, you can open more sockets. But in this context, each client will have one socket through which it's going to connect. Okay, and so it creates a client socket, and then the blue line represents a TCP packet, a connection request going to the connection socket. Okay? And then, like I said, A is in front of B a little bit. So traversing the internet is the connection request for B as well. Now this connection client A is now triggered an event inside the server through the connection socket. And so it's going to create a thread to serve that client, okay, a unique thread to serve that client of that thread, and going to use a server socket unique to client A and pass that back to client A. So now the server socket in the server is a one-to-one connection with the client socket in the client. Okay, and so the next response that originates is going to have a unique shared paired connection. Okay, and so now B is showing up, and so now the A is going to do a GET request. We saw that in the previous slide. Hey, you can see the little red GET, right here is the, hey, what's the weather in Austin? Okay. And down here in B, its request for connection is showing up a little bit after A. And so it will create a thread for B. And now this GET response is traversing the internet. And so this next step, the second socket, unique socket, is going to pair these two, right? You see there's a unique pairing between client socket for each client and a separate server socket and thread serving those requests. Okay. And now B is going to ask for the weather in Dallas or whatever. And so this GET response occurred over here, and this GET is just starting. And so they will process the request here, and then figure out what the weather is in Austin. And down here, this guy is traversing, and he's traversing a little more. And then the response is going to come. It's going to come. There's my response. It's coming in this direction. Then the response is further over. The GET showed up over here. There's going to process the GET. The response is going here. It's going to show up down there. And then your display will say what the weather is. This guy here will then will go further down. And then this guy is now processing, showing the weather on its screen. It's sunny and whatever. And over here, this new response for Dallas is coming and then going this way. Now, in this context here, for this starter code in the weather app for the weather project on the lab, it creates a socket, fetches the weather, looks at the weather, and then closes the socket. Okay. Now you could have left the socket open, but it didn't. It closed it. And once you close the socket, it breaks this barrier, and then this guy here is going to go away. Okay. So here's the cloudy going back. And so once this guy has closed, this server socket is then discarded. And obviously this one's getting closer. And then this response is getting closer. This thread will eventually go away because it's no longer needed. And then this response is going. Okay, and then that thread goes away. So let's ask some basic questions. What did the client do to create a thread here? And what created it, what used it, and what destroyed it? Do you see? That's what you should have gotten out of this animation. What event caused the thread to be created? How was it used? And what caused it to be destroyed? And that includes the server socket. So what created the thread and server socket, what used it, and what destroyed it?
Oh, are you asking us?
Yeah, I'm asking you this question. Yeah.
Oh, when client A connected to the server.
Yeah. So the first connection event, right? Here we go back in. Right? This first connection event here, the first time you connected to the server, you went through this open connection socket. But the next time you go through, it's going to go through the server socket. Okay. And then how you used it is you sent GET request. Okay. You sent GET requests. What event caused the thing to get destroyed? What will cause the thread and therefore the server socket to be disabled, to be discarded?
When the client closes.
Yeah, the close event in the client is going to trigger a signal back to the server saying, thank you very much, I'm done with you for now. Okay, so this close event here will close the server, close that server socket. All right. Okay, so there's the GET response. Oh, yeah. Did I tell you the other day I had an epic failure? I was so trying to do this. Okay, so I'm gonna do it. I'm gonna click on this thing anyway. Okay, connection. Okay, server. I can't do it this way. Client server not responding. Okay, whatever. Escape. Stop share. Crashed. All right, cancel. Crashed. All right, I'm gonna kill that. There it is. Okay, go. Okay, fine. Eventually made it. This was Yerubali created this server for us on the MOOC, and I was completely unsuccessful in recreating it for you guys this semester. But this is, okay, let's see when the data was. How long ago was this taken? Oh boy. Okay, no, that's a different one. Oh no, that's embedded system server. That's a different. Okay, this one is, like I said, this was lab 16 on one of our edX MOOCs. And these were people who were getting their lab 16 graded. And so, yeah, we were able to draw maps, but like I said, yeah, it's epic failure. I couldn't get this thing to run. Okay. All right, so next I'm going to go, next thing I'm doing is going to show you how what some of this code looks like on the, okay, I got 5 minutes, I got 10 minutes left. Okay, questions on that? So which I wanted you to get out of there were sockets, connection socket, server socket, client socket, JSON, GET requests. Those were the TCP layouts. I'm going to drill deeper into how the lab works here with the CC3100 booster pack on top of the MSP432. That's obviously a TM4C. Okay, and like I said, my first foray into my first adventure into, well, it wasn't my first. Wow, a fun adventure into Wi-Fi was this massive open line class that I did with Yerubali, chapter 16. Yeah, okay, so it's running. We saw the the client server in the last video, and now we're going to show you some of the code. Okay, here's a block diagram of the 3100. Basically, when we, just like all the other IoT devices that we've done all semester, we're going to push down into either a separate processor or into dedicated silicon the physical and MAC layer. Okay, so the physical radio and the media access controller are done in silicon at a low level. That will drive the cost down. That'll drive the the functionality up, the size down, the power down, all the cool stuff. And so this particular protocol, this particular architecture had the two choices, just like Bluetooth and sub gigahertz, is we could have put the entire implementation on a single processor and then just implemented the stack, the layers within that single chip. Or in the context, or in this one, it's done with a 2-chip solution. The Wi-Fi network processor, okay, with the MAC layer in it. Now it turns out we're going to go even further and add even more layers into this dedicated firmware, okay, such that our external microcontroller is so stupid it doesn't really have to do with much at all, okay? And that's the architect for this particular, which is what you do whether it's a single chip or a dual chip solution, is stack. A layered system means the layers are separated. And whether they're separated physically here, the layers are separate physically with 2 different chips, right? This is the CC3100 and this is the MSP432. Or they're separated in a single chip. They're still separated. There's still a stack associated with it. Oh, I don't know. I haven't asked her yet, but I'm gonna find somebody to come talk about antennas. There was an antenna on the last exam. I don't know how to ask you an antenna. I don't know how to ask you a question for the Wi-Fi antenna, except that there it is on the printed circuit board. It's a 4-layer. It's a 4-layer PCB. You've got signal on this layer. You've got signal and ground on this layer. One of these is a ground layer, and one of these is a power layer. So you got power, ground, signal, ground, power, signal, ground. And obviously it's has to do with electromagnetic waves, so you're not surprised to see a keep out around the antenna, okay? Void space on all layers so it doesn't happen. This is that cute little thing you can attach an antenna to. That's a socket, a connection that you can stick another type of antenna on if you want. And then there's a bunch of stuff that I don't understand. Filters and wave guides. I don't know if there's something in here, wave guide. I don't know what it means, so don't ask me. I'll get somebody to come in here and talk about how you design a Wi-Fi antenna. But this was basically saying the same thing I said earlier, and is if you think about how Wi-Fi works on your laptop or a desktop, basically the MAC layer and the radio layer, the physical layer and the MAC layer are done in hardware, and the Wi-Fi stack is all done in software. And so this has to be a very powerful computer. It has to be a pretty powerful computer to implement TCP, IP, in software, okay? But in order to drive the costs down, in order to make it an embedded device, we're going to shift layers here, okay, into hardware, okay? using a hardware dedicated device. And then that will simplify the software that has to run an embedded system. And so if you look at the starter code or look at the solution that's provided here, you'll see the letters SL. SL represents this simple link communication. And so whenever we open a socket, whenever we do a domain name service, whatever, those are all going to be functions that are fairly simple to use, which basically, just like our Bluetooth example, send the command down to hardware to be implemented at that layer. All right. So I got a couple of examples here. Here's a UDP. Here's a UDP point-to-point. So you've got this particular hardware is you've got a microprocessor, a CC3100 access point to a second microprocessor and a second CC3100. And basically I'm streaming data UDP. Okay. And so when you check out the lab, I'm going to ask you some very fun. I'm going to ask you these. Oops, the other one, it's gone. I'm going to ask you these fundamental questions. Discard. These. I'm going to ask you these fundamental questions. How does it connect to the access point? Okay. How does it, what does it do and how does it request an IP address? What did you do to open a socket? What did you do to send a message? What do you do to receive a message? How do you close a message? Okay, so I'm going to do that with this example here. So embedded, now some of them are better abstracted than others, but here's my I'm going to connect to the access point. I'm going to send in an SSID name, the password, the encryption type. So this has got the fields of this are name of the access point, the password, and the type, the encryption type. Okay. Now in this particular case, it didn't use a domain name service because I hard coded the IP address. Okay. This was a local area network. I could go to the router and I could go to the access point and say, what's my, basically when I connect up to the access point will respond back to the device what its IP address is. And I just copied the connection from the server hard coded it into the client here. So and then when I didn't use a domain name service. So the next thing I'm going to do is create a socket. Okay. And that is done right here. Okay. And what are the components of a socket? The components of a socket are the type. Okay. That's in this that's going to mean UDP, and how it is connected, right? And so this address, the socket didn't have the address and it just had the type. Okay. But you'll see that when I send a message, okay, I'm going to use the socket, okay, right there. And so, this is, a data structure with a lot of fields in it, right? And that's the index into the socket table. Here's the payload. There's the UDP payload, which has got the, you know, the message I'm trying to send. That's the size of the message. And this is where it's going to go. Okay. That is the location to which I'm going to send my UDP packet, which again, I hard coded the IP address and the port number and the type. Okay. And then basically the socket is open here. It's created and opened. It's used and it's never closed in this example. Okay. And then on the server is a little bit more complicated. Well, not really. It's more complicated because it's going to do output to the display. But it does the same sort of thing. It has to connect to the access point, which is here, which again contains the name, the password, and the type. It is not going to send, it's not going to send data. So you'll see that it doesn't, it's got a port, but no address. Okay. It's got, it's got a port, but no address. And so when we create a socket, where's my, okay, so then here's the run. When I create a socket, okay, I am going to, again, this is a UDP packet. And then I'm going to connect the socket with the receiving port. And now I'm just going to wait for data. Okay. I'm going to wait for data from the other device. And then all this crap here will I don't know why I didn't, maybe I just lost it, why it didn't discard the socket. This is just processing it.